Okay, so good afternoon, everybody. So it's a great pleasure to welcome Professor Arun Paramekanti from University of Toronto. He's a professor of physics. So he did his PhD from Tata Institute, took a long back. And then he was a postdoc in UC Santa Barbara and Berkeley. And since I think 2005, he has been a faculty at Toronto. So he's a leading expert in quantum condensed matter theory. And so I think it's a great opportunity for you, all of you, to have these lectures on this uh, phase transition and renormalization group, basically. Yeah. Okay. And if you have any question, I guess, just feel free to ask him at any point because, yeah.
Yeah. So I'd like to thank Sanjeev for this opportunity. Actually, first of all, visit RRI for an extended period of time, but also they said we could kind of organize the set of lectures for the students. So this is meant to be like a set of 12 lectures, and I think it will be pretty dense. So, but we can slow down so it doesn't have to go, I think, according to the advertised plan of lectures. So just feel free to stop and ask questions along the way. And if people want to discuss, maybe after the lectures, there'll be time. So I'm happy to hang around and if you have questions, right? Or during the lectures is fine. Okay. So let me begin by kind of, so the first lecture today, I'll just do this on using slides, but then we'll switch to the Blackboard for the second hour and then for the rest of the lecture. All right. So what do we, so in some ways, a kind of unifying theme of, condensed matter, and in fact, a lot of science that we know is the idea that, when you bring together many different constituent particles, and this is something you might have heard in, other courses that you've taken is that, there are different organizing kind of principles that emerge as you go to different scales, either length scales or energy scales in nature, right? And many of these, when you kind of go from one level to the next, you kind of discover things that may not make sense at a certain scale, might make sense at a different scale when you start asking these questions. And so in fact, this was first, most clearly articulated in this science, like a news and views type article by Phil Anderson. And in that particular article, he advocated for this notion of broken symmetry as kind of an organizing principle for many of the things that we see in nature. And so, if you look at simple examples, right? So if you talk about a concept of temperature, right? Then from your courses in statistical mechanics, we know that, this doesn't make sense to talk about temperature of a single particle, whether it's a single electron or a single atom is not, or a single electron is not very meaningful to talk about this, but it is certainly meaningful to talk about like the temperature of electron, a gas of electrons in a metal, for instance, or a gas of electrons that might form in stars. Right? Similarly, if we talk about things like fluids, it makes no sense to talk about viscosity of a molecule is a meaningless concept. Once you have some kind of hydrodynamic description that emerges when you put together many of these constituents, then you can start talking about concepts such as viscosity or hydrodynamics. Things like sound. Again, it's some collective vibrations of some crystal, which makes no sense at the level of a single atom. Right? And one would go so far as to say that if the way we think about sort of classical Newtonian physics, one must also kind of think about that as some kind of way where as we go from, let's say, microscopic scales where we have some quantum description to having this collection of a huge number of particles, one should really view this classical physics as also some kind of an emergent phenomena in this way of looking at the problem. Right? And so, in fact, the broad goal of condensed matter, and I'm saying condensed matter here, but really, as I've written here, it's really true for much of science as we do it, is to really try and discover these kinds of emergent concepts, notions like temperature, pressure, notions like, hydrodynamic descriptions, right? And using a combination of basically theory and experiment. And I guess this interplay of theory and experiment is probably most clear in condensed matter physics, but certainly it's also, these kinds of ideas also play a role, whether you're looking at, or in biological physics, for instance, right? Or in high energy systems. And, then the idea is that once you have these phases that can emerge, and we'll discuss this in more detail. You want to kind of understand, how do you think about these phases? How do you think about their properties? And at some level, you might decide that, some of these phases might actually be useful for something, and you want to think about sort of how you might apply some of these properties to something useful, right? So there is some merit to thinking about this in kind of diverse fields other than just condensed matter. Right? So if you think about the concept of phases, at the naive level, you would say, well, it's just based on our ability to distinguish certain qualitative differences between things that we see around us. So for example, we might take a collection of water molecules, and we might say, well, I have something that flows, like water in a river or something, or water from a tap, and you say, well, that has some property that it's flowing. Whereas if you cool water so that it solidifies and becomes ice, and you say, oh, it doesn't flow, right? So that's kind of a qualitative kind of visual distinction that you might keep in mind, and you might say, oh, well, that way I can distinguish these two phases, right? Similarly, if you think about more other things like gas versus liquid, you might say, well, I know that a gas kind of expands to fill up the volume of the container, whereas liquid kind of stays in some fixed volume in some region of the container, right? If you think about metals, right? So now we're thinking about collection of electrons in a solid. You would say, well, if I look at a metal, I know it's kind of shiny. Like if I look at copper or gold, I know it kind of is shiny, whereas and it conducts electricity, right? Whereas if you look at insulators like diamond or something, you'd say, well, it's kind of, of course, it doesn't conduct electricity, but we also know that, oh, it's kind of transparent. I can kind of see through it, as opposed to a metal that, I can't see through a metal. Unless it's like a very thin foil or something, I really can't see through a piece of metal, right? Another distinction you might come up with is, oh, well, I can distinguish, finite resistance, non-zero resistance from zero resistance, right? So there are various of these kind of, distinctions that we might make qualitatively, and a lot of things that we want to do is to try and translate these observations into some more precise distinctions that we can sort of quantify or measure in some way. Okay, and so you can ask, well, what are the kinds of sharp observables, right? And so for this one, I'd say, oh, let me measure the resistance. I know it's either zero or non-zero. That's kind of a sharp distinction that I can measure and see. You can also define, and which leads us to this idea that somehow, can I see something, can I look at something locally, and can I tell the difference between a crystal and a liquid, or can I tell the difference between, let's say, a conductor and a non-conductor? And it'll seem that in some cases, you can try and define this notion of what's called a local order parameter, something that's a local observable. And by measuring this object and kind of, averaging it over space, you kind of get a notion of, are you in phase one or phase two? You could look at differences in response. So for example, you could try, say, well, if I'm looking at, let's say, a solid versus a liquid, I could try kind of shearing this object and see how it responds. Does it flow, or does it have like some kind of non-zero elastic modulus, right? And so you can kind of look at differences in response, or if you apply a current, do you get some measurable voltage across your sample. You could also see, and I'll kind of discuss this more in later slides, there might be sometimes differences which might not be locally observable. So for, prime example of this that I'll mention later is something like the quantum Hall effect, where in some of these cases, you have to not look at, if I look at it locally, I won't be able to, tell that there is something different between, two different phases of matter. But, there are some certain ways in which you can sort of see that there are certain topological distinctions. Something in the global response of the system looks different between different phases, right? And if you look at quantum mechanical examples, in fact, one can go beyond, responses, because you could say, well, in a quantum system, if I give you a Hamiltonian, of course, I can diagonalize this Hamiltonian, let's say on a computer, right? And I can ask about, oh, does the spectrum of this Hamiltonian have a gap, for example, between the ground state and the first excited state, or is the gap, vanishingly small? You can ask more questions. If I have lots and lots of this in the spectrum, there are many, many eigenvalues. I could ask, oh, can I look at the difference between, let's say, the subsequent eigenvalues, measure these differences, and learn something about what phase I am in? Can I learn something about it by studying the quantum wave function for the ground state or excited state, right? So when you come to the quantum case, there are, of course, other than order parameters and responses, you could look at kind of many more detailed properties that you can access, for example, on a computer, even if you can't necessarily access it in an experiment, right? All right. Okay. So I wanted to kind of just walk through a bunch of these. So if people have questions, feel free to stop me. But the next few slides is really kind of illustrating a bunch of phase diagrams. And if people have taken like a course in statistical mechanics, thermal physics, maybe this kind of just repeating things that but I guess it's okay for the first lecture. Okay. So if you think about sort of the difference between a gas versus a liquid, the immediate distinction, which I've kind of illustrated in this cartoon here, is that there's a huge difference in the density between these two, at least like between water and steam at kind of ambient pressures, for example, that we might be looking at. There's a huge difference in densities. But other than that, there really isn't a qualitative distinction. So if I stare at this image versus that image, other than the fact that these have clumped together, I really can't tell there's anything spectacularly different between the two. And so you might ask, well, can I distinguish between these two simply by using the density itself as an observable that I can tell apart one from the other, right? But if you look at other systems, like for example, the difference between a liquid and a solid, or a crystalline solid to be more specific, now I say, well, in a crystalline solid, I have this very specific periodic arrangement of atoms. So even though the liquid and solid have almost identical densities, unlike, let's say, water and steam, they have almost identical densities, but they differ in a symmetry in the sense that if I look at, let's say, a time averaged way of thinking about sort of, what happens if I sit on one atom and I look around me, my environment will look the same, whereas that's not the case if I'm in a crystal, right? And so similarly, if I kind of move from one place to the other, then in a particular snapshot, it might look like this kind of random arrangement. But if I time average over, let's say, short time scales, the density is basically completely uniform. Whereas here, it has this very specific modulation with a very specific lattice spacing between the atoms, right? And so it's, of course, that's one way of telling this in real space. But a very clear way of seeing this in an experiment is to capture the symmetry distinction by just looking at the Fourier transform of these two. One is a constant, one is some periodic function. And so this one will have sharp peaks in momentum space corresponding to the inverse of the spacing between these atoms. And that's how people measure this thing using, for example, X-ray diffraction. You kind of probe this crystal in momentum space. And so you see a sharp diffraction spot at the wave vectors corresponding to the solid. But moving on, this kind of idea of symmetry breaking that I can distinguish between the two also applies to other types of systems. So you could look at, for example, not just the atoms in a crystal, liquid to a crystal, you could also look at, for example, the magnetic moments that an atom might carry. And those magnetic moments might be randomly arranged in what's called a paramagnet, or it might have some kind of broken symmetry here, which definitely has at least the symmetry of the crystal, right? But this pattern here has a symmetry that's lower than that of the crystal, where I can't translate by 1 unit. I have to translate by 2 units before I see that the magnetic moment stays the same, right? And so here you have an example where the atoms are certainly not changing in character, but the magnetic moments, or these electrons sitting in the atom, organize differently, and depending on the solid, of course, right? And in this example, this is what's called Néel order, which is an antiferromagnetic order on this square lattice in this example, where you can define the Néel vector as like a staggered magnetization. So imagine I take this and I take the next one and I flip its sign through this extra factor here. Then, of course, S flips, but so does this factor, so that the Néel order parameter is like a smoothly varying function of space. And this particular simple example is just a constant in space. So you can absorb, this fast modulation of the spin in space by multiplying with this factor to end up with something that's slowly varying. And this will be important when we talk about Landau theories, because the way we are going to formulate the problem later on is to think about things where things are slowly varying on the scale of the lattice constant, right? So you want to absorb somehow these fast variations of any order parameter and try to kind of focus on the slowly varying degrees of freedom that you'll be able to kind of describe its physics at longer and longer length scales. Right? And this also allows us to kind of talk about sort of the symmetry properties, because, for example, you might say, well, this nail vector, for example, if I kind of try and do time reversal or translation, I can sort of ask, what happens to this nail vector, and you can kind of see that under time reversal, it flips sign. The spin, for example, will flip sign under time reversal, and you can kind of see this by looking at the symmetry properties of such an order parameter. So the concept of topology that I was mentioning, in fact, a lot of, in fact, there's some very interesting work that came out of the research here at the Raman Institute. So I was kind of reading about some of this as I was preparing these lectures. But the simplest example of liquid crystal are some kind of, elongated molecules where, I can't tell the difference between head or tail, but, they have some shape that's not like a perfect sphere. And if you do that, then you can actually get interesting transitions where these molecules could be organized such that they're pointing in random directions, or they could all line up to point along some common axis. There is no particular ordering like in a crystal. So the atomic positions are not ordered, but there is some kind of directional order for this. And you can now try and capture this by saying, oh, can I define some way of looking at this directional ordering? Right. And in the particular case of these kinds of rod-like molecules, the simplest way to think about this is to say, well, I can assign an arrow, let's say, that points along this molecule, but I don't know whether this should be pointing up or down. Right? And so you can think of this as a headless vector, or what's called a director field. Right? And now you can kind of try and describe the physics by thinking about, the physics of this director field and say, oh, well, it's kind of random here. It's not ordered in some way, but there is some ordering of this director field such that it points along the north-south direction in this particular plot. Right? But this brings us to sort of a first example where, topology plays a role, because these kinds of, orderings, and we'll see more examples of this later, admit the possibility of what are called topological defects, right? And in particular, this is an example where the liquid crystal molecules are all lined up along a direction. This is one where they're completely random, right? But in an ordered phase, I can also define what are called disclinations. So these are topological defects where if I look far away, let's say the liquid crystal molecules all point north-south, exactly like in the ordered state here. But in the vicinity of this defect, the liquid crystal molecules basically have to turn, not just in the vicinity, but as you go around this defect, this liquid crystal molecules basically rotate from, let's say, being in this direction to pointing slightly off, along the, northeast, southwest direction to something that's flat and then eventually going back up. Right? And so these disclinations are now defects where no matter how far away I go, and here is another example, no matter how far away I go, I know that this is not ordered. But more than that, I know that as I take a loop around here, and I've kind of illustrated with these two red and blue loops, as I go around this trajectory here, I see that, oh, look, it points vertical. It's turning a little bit. And that turning here, I can plot it on the circle where, let's say it starts off at the North Pole, let's say here. I can't really distinguish north and south, so I'm kind of connected them with a dashed line to say that those are indistinguishable, right? And I can kind of start moving down here because this molecule is turning. Eventually, I'll reach a point where it's flat, where I'm somewhere here on the circle, right? And then when I end up back here, then I've kind of turned by 180 degrees. So this line has turned by 180 degrees as I go from here to there, these molecules. And so you see that I've started at the North Pole, ended at the South Pole, but the North Pole and South Pole are basically the same thing. Right? And so these molecules are the same as those molecules. They're pointing in the same direction. And so you see that these defects have some topological structure to them because now, as I go from north to south, imagine I take this loop and try and ask, well, can I make this defect somehow disappear by rearranging these molecules? And it turns out you can't, because there is a certain rigidity to this, where I've started this loop at the North Pole, ended at the South, and now the South and North are the same. So I've ended up forming a loop, which I can't make a local deformation and get rid of it. Okay. And so these kinds of defects are classified using what's called homotopy theory. And in this particular case, these disclinations are characterized by some non-trivial homotopy too. In fact, the work at RRI was, among other things, one of the things that happened at RRI sometime in the 70s was the discovery of not these kind of rod-like, but rather disc-like molecules and certain types of phases where these can form, like columnar phases of these discs, which turns out to be interesting in its own right. Okay, so let's now turn to look at sort of slightly different this thing. So we can ask questions. We've been talking about sort of classical, more or less, things that you can write down without discussing wave functions, right? But if you think about quantum mechanical particles and asking how they can organize, then of course, one very famous example of a phase transition in a quantum many-body system is you just take non-interacting bosons and you cool it below the Bose-Einstein condensation temperature. Right? And what happens then is this sort of picture from some old work on ultra cold atoms, where what is being shown here is the velocity distribution or the momentum distribution of these atoms. And it's kind of this very broad, classical Maxwell-Boltzmann-like distribution to something that has this extremely sharp peak that develops because there's a macroscopic occupation of the zero momentum state as you cool below the transition, where this k equal to 0 mode has some macroscopic fraction of particles kind of end up, or a sort of a non-zero fraction of particles end up in that state. And so that's an example of now a condensation in this quantum many-body system, right? But this leads us to a way of kind of thinking about the order parameter for this example, which is to say, well, if I really think, so one way to say it is, well, I can measure the momentum distribution, right? And maybe I can use that as an order parameter. Is n of k equal to 0? Is it finite or is it actually 0? Is it non-zero or 0? And that would serve to distinguish the two phases, the normal phase from the Bose condensed phase, right? But it turns out that, in fact, you have to look a little bit deeper to figure out what the correct local order parameter is, right? Because if you take the momentum distribution and rewrite it in terms of local operators, then this n of k is really the Fourier transform of one-body density matrix, which is off diagonal. In other words, I take a particle at point r prime, I kind of delete a particle or I annihilate a particle and I create it at point r. So I'm kind of removing a particle from one point here and kind of trying to insert it somewhere else and asking about the expectation value of this non-local object in the ground state or in some finite temperature density matrix, right? And you're looking at the Fourier transform of this quantity. And so if you look at n of k equal to 0, what it measures is this correlator without these phase factors, right? So you're kind of measuring this off-diagonal correlator. And if you want this quantity to scale like the volume so that there is some macroscopic occupation of the k equal to 0 mode, then this particular summation here has to scale like the volume of the system to, like the square of the volume in order to cancel out one factor of the volume here, right? And the way you can do that is to assume that each of these quantities must itself be non-zero. It's some order 1 object, right? And then the two summations over r and r prime give you two factors of volume. Okay. And so you can end up getting a macroscopic number of particles in the k equal to 0 state only if this correlation between removing a particle here, putting it there, somehow splits up into kind of local expectation values of an annihilation or a creation operator. So this, in some sense, is the more fundamental kind of way to talk about Bose-Einstein condensation, that there is a local order parameter, which is a complex number in this case because A and A dagger are not Hermitian operators. Some complex number that takes on a specific amplitude and phase at points in the BEC. And now there are different ways to how do I make sense of this? Of course, if I give you a gas in a box, you'd say, well, the number of particles is fixed. How can I get an expectation value for a dagger? Because if I add a particle, clearly, I've changed the number of particles in the box. And there's at least, two ways you should, think about this. One is to say, well, when I'm thinking about this, I start with some n particle state. I go to some n minus 1 particles when I annihilate one, and then I create one. So I go back to n particles. So you should really think of these as matrix elements between states with different number of particles, n and n plus 1 or n and n minus 1, right? Or you can think that what you've done is you've somehow relaxed this constraint that if I look at some substantially large subregion of the box, there is large fluctuations in the number of particles such that I can actually think of forming some kind of coherent state where giving A's and A daggers is a reasonable. So now, with that, we can turn to, even more complicated questions, right? So you could ask, well, can I tell the difference between an insulator and a metal? So as I said, oh, well, I can, transparent versus shiny. But then you can ask, well, why is it transparent or why is it shiny? And one way to think about, for example, why is diamond kind of transparent is to say, well, there's a huge gap in the spectrum of electronic excitations in my system. So typically, if I have some solid forming a crystal, electrons form bands. So there is some energy versus momentum dispersion relation. Sorry, it is getting partly blocked out, but hopefully you can see most of what is here. There is some energy momentum relation, right? And now you can look at sort of, if the gap here between, let's say, the highest occupied level and the lowest unoccupied level is sufficiently large, then it's like you can pass your photons through without ever being able to excite anything in the solid, right? So the electrons have no way of absorbing or doing anything at all over a range of frequencies, right? So ordinary visible light just passes through this insulator. And so that's why it's transparent. Whereas if you have a metal, then you should really think of, your light hitting this metal, this electron shaking, and then basically re-reflecting this light back to you. And so crudely, photons, if you have some kind of plasma of, these electrons forming some kind of plasma, then so long as you're at frequencies that are not too large, like, less than the plasma frequency, you will see some kind of reflection, okay? And once you exceed the plasma frequency, you can start transmitting light through this thing. The electrons are just not responding fast enough, roughly. So that's a crude way of looking at it. But in the language of bands, you can say, well, why is copper red versus, let's say, some other metals have other colors? And you'd say, well, if I look at copper, in fact, it's not just a plasma, it also has a band structure, right? Some of these bands are, occupied, they're only partially occupied, unlike here where everything below is occupied, everything above is empty. Here, things are partially occupied. So of course, it's kind of metallic at low energies, but you see that, at least for copper, there is a minimum energy I need to give in order to, excite electrons using light. Okay? And so if you do that, you'd say, well, in copper in particular, if you read off this band structure, what this energy is, it turns out that these interband transitions start roughly in the yellow-green light region. So things that are at frequencies below this yellow-green, I can't do these interband transitions. So red light in particular gets reflected, but yellow-green light will cause interband transition, so you won't see it being reflected back to you, right? So you can kind of think about the color of metals more than just the fact that they're shiny. You can start asking questions about the color of metals, but none of this really provides a sharp symmetry distinction or, other than the fact that, oh, there is a gap in one case and no gap in the other. But the question is, can one convert that into some way to more sharply distinguish, other than the fact that, because a gap is some global thing that I measure, right? It's not like a local order parameter. I'm not looking at local gaps and saying anything. But the question is then, can one come up with some suitable order parameter to think about, what distinguishes a metal from an insulator? And I'll just leave that as a question. So the last thing with phases then is, thinking about topology that we mentioned for liquid crystals, we can now start thinking about topology for, systems of collections of fermions, right? And here there's been a lot of work over the last, 30 years on this quantum Hall-like states, where, what you're measuring is the Hall resistance. So this is, you send current in one direction and you're looking at the transverse voltage in the presence of a perpendicular magnetic field. And you see that, oh, I do see signatures in this this quantity, the Hall resistance, that, oh, looks like, there are some plateaus. Sorry, ignore the dips and stuff here. Is really this line here that I want to talk about. So there are things where, for example, here you see that, oh, instead of being a straight line, this has, what looks like flat regions, things that don't change as you change the magnetic field. And so those you can kind of associate with distinct phases of this quantum Hall fluid. So it's some kind of fluid whose, imprint is to say, well, it's characterized by having a certain quantum Hall conductance. I mean, there is more than that, but at the very least, the quantum Hall conductance is one way to distinguish, this from that value. And similarly, there are, more recent discoveries, including, things like these topological insulator phases in 2 and 3 dimensions, where there are certain types of excitations where in the bulk, it might look like diamond, it has a gap, but on the surface, it has certain structure of gapless electronic states with a very specific relation between the spin and momentum of the electron. And so these kinds of phases, if you want to think about them, you really have to think about, what is the nature of wave functions of these, electrons? Are there bulk, topological invariants? And really, again, you can ask, well, is there an order parameter that tells me, oh, here is an ordinary insulator, whereas the topological insulator, is there an order parameter? And again, I'm leaving that as a question here, but really we should be thinking about some bulk topological invariants to try and distinguish one phase from the other. So are there any questions here? Because I want to then kind of move on to this notion of phase diagrams, and that will kind of set the stage for the next few coming lectures. Yeah.
So different things of phases, but if I have something, if I want to decide what do I call a phase or not?
Right. So that's exactly the point, right? So you have to find some way of really distinguishing whatever it is you found from other states of matter as we know, right? So that's precisely the challenge. So if you want to kind of define this thing as a new phase of matter, you would have to ask, does it differ from other known phases in a way that I can measure some local observable and tell the difference? Or can I measure something in the spectrum? Can I see something that differs in signatures qualitatively from other things that are known to us in nature? Yeah. Okay, and that's the general kind of thing that I wanted to say with kind of all this. There are all these different, there are classical phases of matter, there are quantum phases, and I've not even touched upon all the non-equilibrium stuff that happens, which I heard there's another course that Sanjeev is teaching on some of this non-equilibrium phenomena. And there's a whole host of non-equilibrium phases that one can talk about as well, which I've not touched upon at all and will not touch upon during this course. Yeah.
Transparent and like a metal and insulator.
Yeah.
So this energy gap is also highly momentum dependent. So
correct.
I was wondering, like, if you have like most of the momentum where you have big gap, but there is a big momentum. So what kind of material?
Yeah, so you certainly, sorry. So I have talked about insulators versus metals, but there's a large class of these which are semi-metals. I don't know if that's what you're referring to, where you could have certain bands which kind of touch at a few points in momentum space or at along certain lines in momentum space if you're in 3 dimensions, for example. Right. So these are things where you wouldn't see a large gap, but nevertheless the resistance will be some strong function of temperature in general. The conductivity will be a strong, I mean, if I look at frequency dependent conductivity, it will have some frequency dependence. But yeah, you're right. So that kind of does not directly fall under this distinction that I'm making here for simple purposes, but there's a whole class of these semi-metals and now, There's a lot of work on these kinds of, can semi-metals also have some non-trivial band topology associated with them? So there's a lot of these so-called topological semi-metals in addition to these topological insulators that people work on. So wild semi-metals and things which maybe people have heard of. Yeah.
So semi-metals is not semiconductors.
Well, okay. So a semiconductor is like an insulator with a small gap. A semi-metal really is like some kind of band touching or some small overlaps, roughly. That's the right. Yeah. I hope that's reasonable. So once we have this notion of phases, then you say, well, can I think about phase diagrams? In other words, I want to be able to tune certain parameters, and I want to be able to see, can I go between different phases of matter, right? And in so particular, you could ask, well, what are the kinds of knobs that we're familiar with? So the knobs we're most familiar with are things like, well, I can control, for example, the pressure or temperature, or let's say apply a magnetic field like in the quantum hall. I can vary these parameters and see whether I can go between phase 1 and phase 2 and kind of see how these transitions happen, right? And typically the way you control a phase is that, there is some conjugate field that you're, trying to couple to and modify, right? So if you're tuning pressure, for example, you're trying to change the density of the system by, coupling to pressure, you're trying to change the volume, right? Or you could apply a magnetic field, you could kind of tune the magnetization of the system, and you could plot, does this qualitative behavior that we've talked about, does it change, does it jump, does it smoothly kind of go from one to the other, what really happens, right? And what are the constraints on, can we do this or can't we do this, right? So are there some general constraints? So let's again, this is going to be again a bunch of, illustrative phase diagrams of various systems of increasing complexity. And so we'll go through this, one by one, right? So the simplest example is, you take, for example, something like a classical fluid, right? So let's take water, right? And you can, heat it, you can apply pressure to it. And this is a very familiar phase diagram with sort of ice, this kind of steam or vapor phase and a liquid phase, right? And one thing you notice immediately is that, this distinction that we said is between a gas and a liquid was a qualitative distinction in the density. And we see that, oh, this distinction actually, if this phase transition line, this line here that marks the transition between the gas phase and the liquid phase, if it ends, that means I can no longer tell apart the gas from the liquid, right? And so that means as I go, I can kind of smoothly go around here, and I can go from the liquid, its density keeps changing. And eventually I kind of come around this and I come to the gas without really ever encountering a phase transition, right? So if I have transitions where there is no, sharp distinction between them, except this kind of a quantitative distinction, then, I really can kind of tune parameters in a way to go from one to the other without ever encountering a transition, right? Of course, if you're at, typical pressures and stuff, you're not doing this. You have to go to kind of much higher pressures in order to actually to be able to go around this point, right? And so this here is a line of first order transitions that terminates in a critical point, and the critical point will be of interest to us as we go along. But this is an example where I have a line of first order phase transitions which can end, and this end point is this critical point, right? But in contrast to this, we saw that the liquid and solid have a symmetry distinction between them. So there's something sharply distinct qualitatively between one and the other, and that qualitative distinction can never end, right? And so in particular, this phase boundary will never terminate. There'll never be a critical point associated with this particular phase transition, right? So that's one example. Of course, in this particular case, it bends left because we know that you can apply pressure and the volume of the liquid is smaller than the volume of the solid. So you can apply pressure to go from the solid to the liquid. Typically, this line for most systems would kind of bend rightward. So you apply pressure, you go from the liquid to the solid. Another important sort of constraint, and this is again a thermodynamic kind of constraint. So it's not just true for this, but true for any system, right? Is things that you would have learned in thermodynamics, which is something called the Gibbs phase rule, which says that if I have a certain number of components of my fluid, in this particular case, let's say water, so it's like a one component fluid, and I have a certain, I'm asking what phases can coexist in a thermodynamically stable fashion, right? And F tells me, how many degrees of freedom do I have left if I demand coexistence, right? So for example, if I look here, I would say, well, I'm in the gas phase, right? So the number of phases which the number of components is just one in this case, right? The number of phases which coexist is just one, right? And so you see that, if I work out what F is, the number of degrees of freedom, C and P basically in this case cancel, you end up with 2, right? And that means I can vary 2 parameters, in this case pressure and temperature, while staying in the same phase. Okay. If on the other hand, I demand that I want to be at the coexistence between the liquid and the gas, right? That means the number of phases that coexist is now 2. And if you want this to be thermodynamic, this thing constraint tell us that this can only happen with where the number of degrees of freedom is 1. And the number of degrees of freedom is 1 tells me that I can kind of move along this one-dimensional sub-manifold of this phase diagram while remaining in coexistence, where the 2 phases remain coexistence. Similarly, if I want all 3 phases to coexist, I should kind of see that I have no degrees of freedom left, which means that at most I can have like a point where 3 phases can coexist, right? And this sets the thing for phase diagrams of any system that you might encounter. So if anybody shows you phase diagrams where 4 phases meet, you should be suspicious, and either there is something very fine-tuned about it or it's incorrect, right? And so these are the kinds of general constraints that are useful to think about from thermodynamics for phase diagrams, right? But you can ask, well, that was a classical fluid, and as you said, there are some differences between classical and quantum. So you can ask, well, how does a phase diagram of a quantum fluid look like, or what does it even mean to be a quantum fluid? And in this particular case, we can kind of demand that somehow I'm going to define a quantum fluid such that the effect of quantum fluctuations are so large that the system kind of remains liquid-like without crystallizing down to 0 temperature. And best as we know, this only happens really, at ambient under ambient conditions for helium 3 and helium 4, the 2 lightest, among the lightest inert elements that we know, right? And so helium 4 behaves like a bosonic atom because, of course, it has a closed shell, so it has an even number of electrons, right? It also has an even number of nucleons, and so the total number of fermions that constitute this atom is even, and so this has bosonic statistics. So long as I don't sort of bring them too close to each other, it's meaningful to talk about the statistics of exchanging these particles, keeping them sufficiently far away. And if you do that, then you can kind of see that this particular system has more than just the liquid phase and the gas phase and the solid phase. You can enter into these kind of Bose-condensed-like phases, these superfluid phases at low enough temperature. And the reason, of course, this stays fluid is that this is light enough that quantum fluctuations are sufficiently large to prevent crystallization. So if you heard of this Lindemann criterion for melting, you would say once the form a solid and once the fluctuations in the position become a substantial fraction of the interatomic spacing, the solid will melt, right? And so you can kind of ask, well, if I try to form helium 4 solid, what are its fluctuations in the position of the helium atom? And it's large enough that you end up kind of always being in a fluid phase rather than a crystal phase, at least at ambient pressure. Of course, if you pressurize it, eventually it solidifies. Right, so there are new phases that develop like the superfluid phase. But if you take a slightly different one where you say, oh, well, it's still helium, but I'm going to look at a slightly different, just a different isotope. So I've just changed the number of nucleons by 1. They say, oh, well, that must clearly be a fermionic atom because now I have an odd number of nucleons, still an even number of electrons. This still, I mean, its mass is more or less the same as helium 4. So everything that applies about it being fluid down to low temperature is still the same for the 2, right? But in this case, you see that because there is a dramatic difference here between the phase diagrams here and here. So of course, I have plotted this on, here I've taken figures where this is now looking at extremely low temperatures, somewhere down here, where instead of forming a superfluid, it stays a normal fluid, right? But eventually it enters into not a Bose condensed phase because these are not bosons, but some version of a superfluid phase where these fermions must pair into bosons. and Bose-condensed, right? So that's the rough way of thinking about the superfluidity of these particles. And so this tells us, okay, if I have a quantum fluid, I should also be able to tell the distinction between Bose statistics versus Fermi statistics. And of course, there's a lot, beyond helium that people probe with cold atoms. There's a huge number of these experiments which see this dramatic difference in the physics of these two. There's another cool one which I couldn't resist showing this, although it is not kind of really central to our talk, is that there are, helium-3 also has a nuclear magnetic moment. Okay, and so there are interesting things in the phase diagram of helium-3 that are not found in helium-4, where if you take helium-3 at some substantial pressure and you try to heat it, then there's a regime where it goes from a fluid phase into a crystal phase. And this is very unusual because you'd say, well, as I heat the system, somehow it's kind of getting disturbed more. So how can the solid form at higher temperatures and the liquid at lower temperatures? Right? Actually, have people seen this, or do people know of what's this thing called inverse melting? So this is a very interesting phenomenon where the main thing is you want sort of your high temperature phase to have more entropy, right? And so what we're saying is, well, the solid phase, as I go across this boundary, must have higher entropy than the liquid phase, right? And normally this wouldn't make sense if the only degrees of freedom are the positional degrees of freedom, because clearly you've stuck your atoms, the entropy has gone down, right? But in this particular case, helium-3 actually has nuclear spins. And if these moments can be disordered, then you can get a huge amount of entropy from the disordering of these local moments in the solid phase. In the fluid phase, it forms something called a Fermi liquid where the entropy is actually low. So it turns out if you're in a magnetically disordered solid, it actually has much higher entropy than in this fluid phase that you have here. Right? So the normal liquid, in fact, you can get this what's called inverse melting, where you heat and you crystallize the system. And that's perfectly reasonable. It's kind of rare, but happens. So here are kind of more examples. So you can have, we've looked at some, but you can have a huge diversity of these things where you say, well, there are magnetic systems, there are superconductors where in addition to temperature, pressure, field, I could change the chemical composition by doping it, right? There are also examples of phase diagram with nuclear matter where I can change the density of nucleons and I can change the temperature. So if I kind of smash, let's say, nuclei into each other, I can sort of give them a lot of energy and kind of really heat up the system. So I can have a very hot gas of nucleons, which people kind of measure in some of these collider experiments. Like this is like some thing where people can do this heavy ion collisions in experiments. So you can kind of access these things. There are also, examples where you can get extremely dense nuclear matter, which is of relevance to stars. And now you can start asking, if you have a neutron star, it's formed of these, quark matter, does it have this nuclear matter? Can it have phases like superfluid phase or not? So the idea is that, this phase diagrams that we talk about, if you kind of think about, completely different types of stuff at pressures and temperatures that have no analogs in a lab, you can still make sense of the similar ideas and concepts will apply across these systems, right? So that's one thing. The second thing that we'll see is that, here we've kind of accessed phases by tuning temperature, but you can also sit at very low temperatures like here. For example, imagine you go down to T equal to 0 hypothetically, but really at extremely low temperatures, and you could start scanning across this phase diagram, encountering what people call quantum phase transitions, where, it's not thermal fluctuations, but really the fact that you have some, your Hamiltonian is made of a set of quantum, operators that don't commute. And so one operator can sort of cause fluctuations in something that's not, commuting with it, right? And so you can get sort of quantum phase transitions as you tune things other than temperature, right? So there's two, things which will kind of lead on to, what we want to talk about, which is, what is universal about this? It just looks like a whole mess, right? Because, here is a material, here is a phase diagram, here's another material, another phase diagram, right? And, there's nothing clean or nice about it if it's like doing different, every time you give me something, I try to look for the phase diagram and then I move on to the next material. It's like there's nothing particularly enlightening about it, right? But in fact, a very nice and early, actually part of his PhD thesis work by van der Waals was recognizing that, if you think about the liquid gas transition, right, you can think about it by a very slight modification of the usual ideal gas law. Right? Where you say, well, I can take pressure and I say, well, if there are attractive forces between atoms, it kind of modifies the pressure that I should have by something that's related to the interatomic interaction. And here V is like the volume per molecule. So it's V total volume divided by total number of particles, right? And or the amount of available volume per molecule, right? And you might say, well, and if the molecules are not ideal point-like objects, but have some size, and you say, oh, well, the size, the amount of available volume is kind of reduced relative to an ideal gas setting. But then you can kind of say, well, maybe this is a modified equation of state that's different from the ideal gas, right? And if you do this, then you say, well, I have some equation here where if I tell you pressure and temperature, I can kind of try and work out what this volume per molecule is, right? And you see, oh, well, this is a cubic equation in V. And in particular, I would say, well, I want to have 3 roots for a cubic equation, but there are 2 cases. One where you say, oh, well, there's just one real root, and there are 2 complex roots. So I should really focus on that single real root. So that's like one particular volume. But I could also have multiple real roots, right, for this cubic equation. And that will tell me that, oh, I can have possibility that, I can have large and small volumes of the system, where a large volume per atom or molecule would imply that I'm in a gas phase, and a small V solution would be like I'm in a liquid phase, right? And so what van der Waals recognized, and again, this is something that, I'm hoping people have at least seen some discussion of in earlier courses, is that, you can kind of, rewrite this problem by saying, well, I'm going to try and march towards this critical point that we talked about for this gas liquid problem. And if you're at the critical point, it turns out that these 3 roots, the 3 roots of this cubic equation must coalesce and all become the same at that special point. And now you can say, well, what is that special point? It happens at a certain critical pressure, a certain critical temperature. So it's some special point in that PT phase diagram. And at that particular pressure and temperature, there is some critical volume per molecule, right? And if you recast this equation in terms of by saying, well, I'm going to talk about some reduced pressure, which is pressure divided by this critical pressure. There's some reduced temperature, which is T divided by TC, and so on. Then you can recast the equation of state that we have here in terms of something that looks universal. In other words, I have lost information about these microscopic quantities like A and B that I don't know what they are for a given molecule. But I have traded it for quantities that I can actually measure in the lab. So I can trade it for a measured critical pressure, a measured critical temperature. And once I do that, it looks like I have a universal equation of state, right? So this is what, he and others later called it kind of the law of corresponding states. In other words, I can kind of, by doing a suitable scaling of my parameters, I can arrive at something that looks kind of universal. So this should apply to all gases in the system. So this is the first example of what you might crudely call renormalization. It's a way where you've taken some microscopic parameters that you don't know about, right? Which, how do I measure something like B? I have no idea what it means to, what B means, because I don't know exactly how much to calculate as excluded volume. I don't know what this A is. I'm kind of looking at the impact of some attraction on the pressure. I have no way how to make sense of that, but I can trade those for things that I can measure in a macroscopic or large, length scale setting. I can measure PC, I can measure TC directly, right? And once I do that, then I have traded what I didn't know for something that I can now measure, right? And so this is an example of renormalization where you can kind of trade unknown microscopic, variables or coupling constants for things that you can actually measure in a lab to fix certain things. And once you fix certain things, then you find that there is some kind of universal behavior. In fact, this is experimental data from an old paper. Sorry, this bottom is getting cut off, but this is an old paper from 1945 by Guggenheim, where all he's doing in this case is collecting data on various fluids and kind of putting them together and showing that, look, if I look at temperature versus, in this case, not the reduced volume, but a reduced density, which is like the inverse of the volume per particle, then there is a certain van der Waals prediction for this universal, from this universal equation of state. And you see that even though all these points don't fall on that line, right? Nevertheless, all these points corresponding to these different fluids actually do fall on top of each other, right? So it tells you that the equation of state is wrong, but this idea of universality is actually correct. Okay, and that's very important because when we kind of go on and talk about renormalization, we'll see that in fact, the precise, mean field or these kinds of equation of states could be wrong. But nevertheless, this idea that there is something universal turns out actually to be a truth. Okay. So let's I'll end with kind of a second, yeah, sorry. This one?
Experimentally,
Yeah.
so while when we're trading these A's and B's for these scaled pressure, temperature, all that. So experimentally, how do these people find, because we need to find PC, TC, and V for doing that, right? So how do they?
VC is determined, actually. VC is, in this case, I mean,
Yeah.
there are two independent degrees of freedom.
So how do they experimentally find this critical point?
Okay, so the critical point, I mean, literally would be to look at, for example, this is kind of a theorist version of how they would do it, right? Is to say, well, I can try and sit at a fixed pressure and kind of try and tune the temperature. So imagine I have a way of, sitting at a certain temperature. Let's say I sit at some isothermal this thing and I just compress and do some isothermal compression and I ask, can I go from the gas to the liquid? And I can try and measure what the density change is from going from here to there, right? And now you ask, well, that density change is huge here. It decreases, eventually it vanishes beyond some point, right? And so the place where this density jump in some sense between the liquid and the gas phase vanishes is one way of doing this, right? It turns out that there are other things that people measure. So there's something called critical opalescence, where actually when you get close to the critical point, you can kind of physically, you can kind of observe that there are dramatic changes happening in the character of the fluid in the vicinity of this point. But that's not, I mean, that won't tell you quantitatively where this is. I mean, it will tell you that you're somewhere in the vicinity of that phase. Okay, so maybe that's not a very good answer. Maybe there are experimentalists in the audience here who have a better sense of, how precisely, one is measuring this, these kinds of phase diagrams. Yep. Say again, I didn't understand. Oh, sorry. Oh, this one here. Sorry, yeah. Yeah, then I will not cancel off this A and B. It won't cancel the A and B, right? So if I pick some arbitrary, okay, so that's an important, which I can't just pick some arbitrary scale to do this renormalization. Right, so in this particular case, you see that, by picking a certain normalization factor, right, which I can kind of sharply measure these quantities because the critical point is kind of a well-defined endpoint, right? It's a well-defined point with a very specific pressure and temperature. So it kind of defines a very special point in the phase diagram, right? And in this particular case, you have to kind of divide by this very specific thing in order to get rid of, quantities that are these kind of microscopic scales. Yeah.
I mean, just look at the equation, because at the end of the day, the conclusion was that, okay, for any A or B, now the reduced form of this equation will look the same.
Correct.
So then is it lying on this sort of assumption that, okay, for such a cubic equation, there will only exist a single triple root point, because there are two triple root points for a.
Correct. So, right. So good point. So for example, if I have anything more than 2 parameters specifying my problem, right? I mean, why do I think that 2 numbers are enough to specify a gas of interaction between molecules or something, or the sizes of molecules? Because the interactions could be pretty complicated, right? So you could have some, Leonard-Jones potential with some complicated bunch of parameters there, right? And so in general, it's not clear that you only have two parameters in the first place to define this equation of state, right? Microscopic parameters, right? So in some ways, this is a very crude way of renormalization, right? A crude example where I only have two parameters and I have two things that I can measure. And so I can take those two and kind of trade them for these two, right? But if I had, like, let's say 3 parameters here, I couldn't have done it, right? And so you might think, oh, well, then universality should break down, because how can I trade 3 parameters for 2 parameters? And so it can't be universal. The physics can't be universal. Okay. And we'll see that that's not really true. In other words, I can start with microscopic theories with many, many parameters or coupling constants. And in fact, the physics near the phase transition, especially near these critical points, is still only described by, a few parameters and not like a huge number of degrees of freedom. So you can still do renormalization. This idea of trading certain quantities for other quantities, you can still do it in the vicinity of a critical point, because certain microscopic parameters will actually not be important. It's what are called irrelevant, and we'll kind of see this later on as we go along. Yeah. Why should it exist? Okay, why should it exist is kind of a, yeah. So one way of doing it, and we'll see this again later on, right? Is it turns out that, especially if we are near, so I'm kind of using this as an example because here is a critical endpoint, right? It turns out that near this endpoint, it turns out that there is a certain length scale called the correlation length, which becomes extremely large, right? And you can kind of think of a process of kind of progressively zooming out, where you're not looking at the microscopic details. You're really trying to say that I can kind of remove these microscopic details, don't matter, because I'm really interested in the physics on the scale of correlation lengths, or maybe somewhat related to correlation lengths or larger, where these microscopic details you would think do not matter. Okay, that's a crude thing which will kind of make it more sharp as we go. Right? But that's the idea, that somehow there is some length scale that is not related to the lattice constant or the spacing between atoms that emerges in the vicinity of this critical point. And having this large length scale somehow allows us to think that all the physics can be expressed in terms of some coarse-grained degrees of freedom, which do not care about whether it's some molecules of carbon monoxide or water or something. I think for polar fluids, actually, this Van der Waals doesn't work very well, but yeah. Oh no, this is experiment. Sorry, this is an experimental phase diagram. Yeah. Theorists would never put, I think, numbers. Yeah, no, this is experimental phase diagram. I think it's a cartoon of an experimental phase diagram, but it's real data. Yeah. All right, so let me maybe end with this last bit here. Actually, should we take a break, or what's the, like, it's like a couple of slides. Are people okay if we just finish it, and then maybe I won't do everything that I plan to do in lecture 2 for today, but I'll just finish and then we can take a few minute break. Yeah. So this is, what was work done by Yang and Lee back in the early 50s, where you try and say, well, here is another way. Why should I think about fluids in the continuum? It's harder because I have all these degrees of freedom which are kind of smooth and continuous. Let me try and put it on a lattice where I can now do some counting or use some ways to actually calculate the partition function and get free energies and so on by putting this thing on a lattice. Because in the end, for a fluid, you'd say for a classical fluid, really the momentum degree of freedom is not really important. You can say, well, I can integrate it out and really look at sort of interactions between atoms at different positions. And so if you really care about that, I might as well put these things on a lattice and try and see what happens, right? And so you imagine kind of these atoms now, instead of moving in the continuum, they're sitting at certain points on the lattice as shown here. And let's imagine that the repulsion between atoms at very short distances is so large that no two atoms can sit at the same point in space. So then you end up with this constraint that, either there can be 0 or 1 atom at each site, right? Due to this hard repulsion, but clearly there is this tail of the attractive interaction between atoms that can cause them to kind of want to come close to each other. So you say, oh, well, there is some interaction that's attractive. And in this case, let's just imagine that it's at the nearest neighbor, but in principle, it could also be, further neighbor interactions, right? If you have some attractive interactions, and in general, if you have some chemical potential, you can kind of tune the density of these particles. Imagine there's some chemical potential. So it's connected to some reservoir where particles can come or disappear from this lattice. But then they said, okay, let's try and define a new variable, which is 1 minus twice the number of particles. Then you see that this quantity, if n is 1, then it becomes minus 1. And if n is 0, then it's plus 1. So this particular quantity here takes on a value which is either plus or minus 1, okay, corresponding to the 0 or 1 atom. It's some two-state system eventually at each site, right? And if you just rewrite this interaction using this change of variables, if you rewrite the Hamiltonian, then it takes the form of what's well known to be sort of an Ising model. In other words, it takes the form of, sigmas being plus or minus 1 are like spins sitting on neighboring sites, which can kind of interact with one another. So you can think of this as some model of magnetic moments being up or down, interacting between neighboring sites with some interaction that tries to want them to both point both up or both down. So some kind of ferromagnetic interaction in this magnetic language, right? And the chemical potential and this combination of interactions give rise to what looks like a magnetic field acting in this magnetic language. Right? So it wants, the SIGA. So there is something where the magnetic field points in a certain direction and wants to, let's say if this quantity is large and positive, then it wants all the spins to be up or plus 1. Right? And so you see that you can trade the Hamiltonian for this fluid on a lattice into a Hamiltonian that looks like a magnetic Hamiltonian of spins. And in this language, you can kind of read off what the two phases are, because if I have something that's predominantly all up, right? Where you have lots and lots of atoms, imagine this thing is filled with atoms at every site, then it's like a dense system, right? A dense system, you'd say, oh, that's like a liquid. That's where n is all 1. But if n is all 1, then sigma is all down or minus 1, right? And so you would associate kind of the state where all the spins are down with a liquid phase, okay? A phase where all the spins point up corresponds then to the gas phase, because if n is all 0, or if n is very, very small, they would say, well, it's a very dilute fluid, and if it's a very dilute fluid, then sigma is mostly up or plus. And so you can associate the up and down, regimes of this magnetic model with a gas phase and a liquid phase. Right? And so you can think now that, okay, what happens in a magnetic system? You would say take something like iron, you cool it down, it orders magnetically. And in this particular Ising-like system, this magnetic moment can either point all up or all down. Those are the true kind of broken symmetry phases of this Ising model, right? But if you're at very high temperatures, then this magnetic moments do random things at each side. They don't particularly care about what the neighbors are doing. Right? And so there are, in some sense, this kind of paramagnetic phase at high temperature and a ferromagnetic phase at low temperature in this magnetic system, where the ferromagnet could be all up or all down. And that's kind of on this line, there is kind of a spontaneously broken symmetry. And we'll make that more clear. But if you apply a little bit of a field, then you favor either a gas or a liquid field. Right? So this is the second version of universality, where they said, well, not only are different fluids like each other, which is what Van der Waals had shown, but in fact, even systems that seem nothing like each other, a magnetic system and a fluid system of fluids, could in fact also share some common properties. And in particular, again, we'll see that in the vicinity of the critical point, there is a reason why this happens will become clear when we turn to Landau theory.
For Ni, you increase Ni, so you should go to the liquid phase. But will that be ordering?
Will that be?
Like ordering can come, because if Ni is very high, then all the lattice points.
Correct. So how do you make Ni very large? Right? So you kind of tune your chemical potential or do something. Right? Or you would have to go to very low temperatures where it would be either all up or all down here, right? And let's say zero magnetic field would be like sitting on this line, right? So this, by the way, this is exactly half Vz is, half Z is this point here. So that corresponds to a vanishing magnetic field is this point here. So of course, if you come down to very low temperature, you say, oh, there is a huge difference in density between the gas phase and the liquid phase. One of which is kind of all up. So every atom, every site has an atom or no site has an atom, right? So that's like a huge density difference when I go a little bit above and below. Or if I'm sitting on this line, then there are two solutions, one which is all up, one which is all down, which are basically have the same energy in this particular case, right? So that's like a coexistence line in the liquid gas liquid. All right, so just to kind of, so what's the aim of this course really is to try and understand this kind of universal physics and this, and we'll see that this language of quantum field theory is actually will have a close connection with things that we will talk about near the phase transition, because we will formulate in a second kind of a free energy, or what's called a Landau free energy for the problem in terms of certain local fields, which are like these order parameter degrees of freedom, and we'll make that more precise. And the resulting theory will look very much like a field theory, where you say, well, there are some fields which are, let's say, slowly varying in position, not in time, because we're just not talking about any dynamics here, but slowly varying in position. And now I have to kind of look at, if I want to calculate free energy partition function, something I have to basically integrate over all possible functions. So it's a little bit like what you might do in otherwise in field theory. Okay. And we will try and identify these phases and phase transitions with fixed points in some space of couplings, which again, in the van der Waals case, these are these like, A and B that we talked about, but more generally, we'll talk about sort of, more general set of couplings and how these different couplings, as you look at it at higher and higher scales, can somehow flow in some dynamical sense, and we'll kind of see what it means. Okay? And here I couldn't resist, paraphrasing something that Deepak Dhar had told us when we were students, because as a student, and maybe this is not true for you, but certainly it was true for me, is that you'd start with some thing where you say, well, I can use a microscopics to understand something, right? And you feel that that's kind of a superior way of doing things because you have provided a microscopic basis for understanding, some phenomena that you observe, right? But on the other hand, what Deepak was pointing out to us when we were students is, in fact, there are certain things that you do which you can never justify with microscopics, right? So you can never really say, well, take this lattice gas model that you talked about, and who is going to believe this lattice gas model is a real description of fluids? Nobody will believe it, right? But in the end, it's the phenomenology that somehow justifies a kind of microscopic approach that you, in other words, if you try and use a certain technique or a certain approach to understand the problem, it's really, in the end, it's like the phenomenology has to allow you to basically do this. Otherwise, you'll end up going wrong, okay? And in some ways, we will see that there is a phenomena of scaling and universality at phase transitions, which is observed near the critical points. And in some ways, that justifies why we can get away with doing certain, what will turn out to look kind of like crude ways of capturing this phenomenology, which leads to this idea of this renormalization group picture and to kind of describe this. So I couldn't kind of resist, including this quote from Deepak, which I had heard when we were students. Okay, so I'll stop here. Okay, and maybe we can take like a 5-minute break. If people want to use the restroom or something, we can just take a 5-minute break, and then I'll continue on the blackboard and at least kind of sketch out this basic idea of Landau theory, and then we can kind of start. Is that fine, Sandeep?
Yeah.
That's fine. So yeah, so it's like 3:15, so 3:20. Should we make 3:20? Like a 5 minutes break if people want to.